So the next one is 41. Actually, I am skipping some exercises before this that are there in the text, but those involve some graphs and those involve figuring out some slopes from those graphs. So they are left to you. They are not that difficult. Instead, let's look at this. Excuse me. In these last few exercises, you have to use some computer algebra system to perform these steps. Now, what the steps are just this. You will be given some limit like this, the function whose limit you are trying to calculate. You have to plot that function near the point x naught that is being approached. For example, here x naught is 2 and the function is this rational function, quotient of two polynomial functions. And then from your plot you have to guess the value of the limit, and then in part C you have to do it symbolically, that means algebraically, and see how close your guess is to the actual value. So let's go through the solution. Now if you do not have computer algebra system or some such software, you can of course always use that online graphing facility, Desmos graphing calculator. So there itself you can draw the graph and see what the limit is. You can guess from that graph what the limit will be. So we are going to go through part C only. So let's see the solution. We have, so straight away we just start calculating. The numerator can be factorized, of course, like this. This is, if you can easily recognize what this is. This is the square of x squared and minus 4 square. So it is x squared plus 4 times x squared minus 4, which itself can also be factorized as x plus 2 times x minus 2. Now you can of course cancel this x minus 2 from the numerator and the denominator, and that is possible because x is approaching 2, x is not equal to 2. Okay, this I am repeating, and I will keep on repeating this fact, that when you see a limit like this, there the independent variable x is never equal to 2. Okay, so when you see something like this, because if you can clearly see that if x is 2, this becomes meaningless. So in this symbol, x is not equal to 2, and that is why that this cancellation is possible. And we just simply have this. And now it turns out that if x gets closer and closer to 2, then this product gets closer and closer to this. See, here there is no point, here there is no problem in substituting 2 for x, of course, because you can just put x equal to 2, but that's not the point. X is not equal to 2. The limit of this is equal to this as x gets closer and closer to 2. So this is 32. So that is the limit. Now if you draw the graph and see what goes on near to, you will see that the value of the function will be near 32. Next, 42. And the 42nd one is another such. X tends to minus 1, x cube minus x square minus 5x minus 3 divided by the square of x plus 1. Okay, so here also we have to do something like that with the numerator so that we can get rid of the denominator entirely. But unlike the previous one, here you cannot have it so readily. It's not factorizable in that sense, but something else can be done. So what we are going to do is that we will try to bring x plus 1 whole cube in the numerator, and then we will adjust whatever has to be adjusted. Let's see what happens. So for x plus 1 whole cube, we need x cube plus 3x square plus 3x plus 1. This is what we need. Now we already have x cube, but we originally have minus x square, and here I have written 3x square. So I need to write minus 4x square. Originally I have minus 5x, here I have written plus 3x. So minus 8x. Originally I have minus 3, here I have written plus 1. So I need to write minus 4. Okay. So now what we have, this part of course becomes the cube of x plus 1, and from the rest of the terms, if you take minus 4 common out, then you are left with x square plus 2x plus 1. X plus 1 whole cube minus 4 times x plus 1 whole square divided by x plus 1 whole square. So now we can do the cancellation, and that will give us x plus 1 minus 4. And this limit of course is minus 4, because as x approaches minus 1, x plus 1 approaches 0. So x plus 1 minus 4 approaches minus 4. Next, 43. This is cube root of 1 plus x, because of which it looks somewhat complicated at first, but then you realize what is going on. Here x is approaching 0. We may be if we become quite familiar with this type of problems, we may be tempted to immediately go for a solution of these limits. That is, you just simply start doing this. But keep in mind, you have to first of all, according to how the exercise has been set up, you have to first of all draw the graph and then at least see what is going on in the graph. And then you do this and then you match your actual limit result with whatever you guess from the graph. Okay. So here, because we have cube root, we cannot get rid of it unless we have a cube. So what I am going to do is this. I hope I have enough space for this. Square plus let me write plus 1 here, divided by, because I have written this extra term in the numerator, in the denominator also I have to write that. So what is it that we have written? It's the square of this cube root plus the cube root plus 1. Now you can see why we have done so. This is, say you call this A and this one as B. Then what we have written here, or what we see here in the numerator, is A minus B times A square plus AB plus B square. AB, because there is a this can be written as a product of A and 1, and 1 of course is 1 square, so that becomes this. But you note one more thing, we have just multiplied and divided by this quantity. You have to make sure that the quantity itself is non-zero. As x approaches 0, is it possible for this to be 0? Obviously not. That is why we are able to do this. And now we have this. Okay, so cube root and cube, they cancel out. Now you can clearly see that if I do not write those steps, 1 and minus 1 vanish. After that, x and x vanish, because you can cancel x, as x is only approaching 0, is not equal to 0. So I can directly write this. Now as x approaches minus 1, 1 plus x approaches 0. So this entire expression approaches what? It approaches 1 because the denominator approaches 1. So this becomes 1. Oh, what? No. I have the previous problem on my mind. It is x approaching 0 actually. Why did I take minus 1? Oh, so if x is approaching 0, then this approaches what? 1. This also approaches 1, and this is already 1. So the entire expression approaches 1 over 3, not 1. Next, 44. X square minus 9 over square root of x square plus 7 minus 4. So just like before, this can also be done as the factor we have written both in the numerator and denominator, that is this thing, is never 0. For no real number x will this become equal to 0. So in the denominator we have this itself, and now as x approaches 3, x is not equal to 3, so x square is not equal to 9, and that is why you can cancel x square minus 9. But there is another point that should be commented on here, that is, you see, x is approaching 3. That means x is not equal to 3. So that's why I am concluding that x square is not equal to 9. But that is not quite true. X square can be equal to 9 if x is minus 3. That possibility is there. But usually when we are talking about limit, the thing is like this. So this is your 3. So your x is very close to 3. So that minus 3, which is somewhat far away from from 3, can always be avoided because x is getting closer and closer to 3. So if it happens that x is coming from here, it starts its journey, then it reaches minus 3, but there is no need to start, there is no need to consider x here and then you move x towards 3. Not in that way. What limit means is that x is already very close to 3 and then we see what happens if we take it even closer to 3. Keeping in mind that we are never taking it equal to 3. So in doing so, what we mean is that we can always start at a stage where this type of problems can be avoided at the beginning itself. Okay, so that's why when we have this, not only is it the case that x is not equal to 3, but x is also not equal to minus 3, right? And that is why x square is not equal to 9. So this step is a legitimate step. Now this of course approaches this. So you have 16 under radical. So that means 4 plus 4 is 8. Next we have 45. This one involves trigonometric functions. Now we will have to apply trigonometric identities that we have already come across in the section on trigonometry. But something else also we will need, which is not to be found now itself. It will come only much later. Let me start the solution. It will become clear what I mean by that. Our aim is always in such limits to get rid of the problematic terms. Here we have two problematic terms, x and sin x. So the thing we are going to do here is this. And why are they problematic? Because as x approaches 0, both x and sin x approach 0. So in place of the numerator, if you go back to the trigonometric identities, you will remember that there we came across half angle formulas. So in place of 1 minus cos x, you can write 2 sine square x over 2, and in place of sine x, only just sine x, you can write 2 sine x over 2 cos x over 2. Now, unless you use these formulas quite frequently, it's unlikely that you will remember them. Okay. So what to do in such cases? Say you don't remember what these things actually are. You have some vague idea of what the formula should be, but you are doubtful. Is it really this? Is sin x really this? Then keep in mind that you do not have to memorize trigonometric formulas. You can always derive any formula you want from this first few. The one that is very easy to remember, and that is something that we always know, is this. Right, this is something that we know, and it's a consequence of the Pythagoras theorem and the definitions of sine and cos. Now, if you divide on both sides by cos square x, you get the formula that tan square x plus 1 equal to secant square x. And if you divide on both sides by sine square x, you get the formula 1 plus cot square x equal to cosecant square x. We don't need those things here, but we also have the angle sum formulas, right? Sine x plus y. These are some things you have to remember. Sin x cos y plus cos x sin y. Okay. Now, if you take x equal to y, what do you get? That means in place of y also we are writing x. Then here you get sin x cos x plus cos x sin x. That means 2 sin x cos x. Now, because x is an arbitrary real number, you can replace x with x over 2, and that gives you this. So that's why we have this. And what about this numerator? The numerator can be had from this, from the angle sum formula for cosine function, minus sin x sin y. So here also, if you take x equal to y, what do you get? Cos 2x equal to cos x, that means cos square x minus sin x minus sin square x. Now, if you write in place of cos square x 1 minus sin square x, which of course you get from here, then you get 1 minus sin square x minus sin square x. Now, interchanging positions of this term and this term, you get 2 sin square x equal to 1 minus cos 2x. And just like here, if you replace x with x over 2, then you get this. Actually, I should not write that this implies this, but I just simply x over 2 So that's how we are getting the numerator. Right. Now, because x is not equal to 0, so x over 2 is also not equal to 0. So sine x over 2 is not equal to 0. Do you see that point coming up here also? The graph of the sine function is like this. No? It goes like this and then again comes down, then again goes up. You understand that this passes through the origin. Now, this point is 0, this point is pi over 2 where it becomes 1. This point is pi, similarly, this is minus pi over 2 at which it becomes minus 1, and this is minus pi. So, as x is approaching 0, actually there are other options also for x at which sin x becomes 0 other than 0, and two such closest options are pi and minus pi. But because this means x is already close to 0, you do not start the journey of x from here or from here, but you concentrate in a neighborhood of 0 that already avoids those points. That's why when we say that this implies x is not equal to 0, it also means that we have gotten rid of the other problematic points. Just like there in the previous one we had minus 3 besides 3, so something like that. Okay, so that means we can cancel sin x over 2 and sin x over 2. And 2 and 2 of course they also cancel out. So that means we have this and this and this. But now what? Now the thing is this, there is a limit, there is a result which you will come across only much later, a standard limit which helps us in such a situation, and that standard limit I am going to write now. That standard limit is this. You can try to see why this is the case by taking very small values of z in your calculator, but keep in mind that this is only the case when z is measured in radian, and that's why when we do calculus where we always need this limit, and this is the limit which we will use in order to prove that the derivative of sin x is cos x, and that fact, since that fact depends on this limit, and this limit itself depends only on the fact that, only when z is in radian, when sin z means sin z radian and not sin z degree. So that's why usually while doing calculus we are advised to use radian measure for angles when trigonometric functions are involved. So this is a fact which we have to just accept now. Now we cannot immediately use it here, but we have to bring this to this form, then only we can use it. And for that what we need is this. Whatever we have as the argument of sine, that exact same thing we should have in the denominator. So because we have x over 2 here, in the denominator also we need x over 2, but originally we did not have 2. So that means we have to adjust that extra thing. Also, we have this. So now we can write our limit. Since 1 over 2 is constant, it does not depend on x. It will stay like that. Now this, according to this fact, approaches 1. So if you want, you can write like this also. This approaches 1. This is 1 over 2. And as x approaches 0, x over 2 also becomes close to 0. And when the argument is close to 0, cosine value is close to 1, because the cosine curve goes like this, and it gets the maximum value 1 at x equal to 0. So the limit is 1. So that means the final limit is 1 over 2. And there is one more, like this. Here also, x approaches 0. In the numerator we have 2x square, and in the denominator we have 3 minus 3 cos x. So here also, just like before, the numerator of course stays like that, 2x square, but the denominator now becomes this. So if you arrange things, then it will, let me at least write the next step, and then we will write whatever extra we need to write. So you can see that we do not exactly have just sign here, but it's square. So here also we do have x square, but that is not enough. We should have the square of x over 2, that means x square over 4. So we are going to adjust things like this. So what we are going to write here is this. You can clearly see that this is equal to that. Now this approaches, only just this ratio approaches 1 as x approaches 0. So its square also approaches 1 square, which is 1, and that's why this limit is this 4 over 3. And in fact, I highly suggest that you actually draw. Draw means you see in those graphing facilities the graph of this one and the previous one, and see actually what the limits, you can guess from those graphs what the limits should be. See if you get values close to this one and this one. You should get, but I haven't seen these particular two graphs. The ones before that, some of them I have seen, but these two particular ones I haven't seen. So you please do that, and this completes this current set of exercises. So in the next calculus update, we are going to see the next section where we are in fact going to go through such processes and many other steps that can be taken in order to calculate this type of limits, to calculate the actual value mathematically. And tomorrow also we have our update. So we have in our cycle of going through these things on Saturdays, that is, we have ring theory exercises from Gallian, group theory exercises from Gallian, and just exercises from Lee's algebra. So we have already gone through Lee once, so tomorrow we are going to go back to group exercises from Gallian, where we have started isomorphisms. So let's see what comes next. So with that, I end the video for tonight here itself. So see you tomorrow with Gallian's group theory exercises. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.